Have you ever stopped to think about what's really happening when a cake bakes, a nail rusts, or you just take a breath? It might seem like magic, but it's actually the invisible engine that powers pretty much everything. We're talking about chemical reactions, and they are going on all around us, all the time. Let's dive in. So, to get us started, I've got a little puzzle for you. I'm about to show you a few things that seem completely unrelated, but I want you to think, what's the one single thread that ties them all together? Okay, think about milk going sour on a hot day, or an iron nail getting that familiar, ugly coat of rust. Grapes slowly, magically turning into wine. The sizzle of food cooking in a pan. Or heck, even the simple act of breathing in and out. On the surface, they have nothing in common, right? Well, here's the answer. They are all chemical reactions. In every single one of those examples, the basic building blocks of matter are fundamentally rearranging themselves into something brand new. It's like the atoms are playing a giant game of musical chairs. So today, we're going to crack the code on these changes so you can start seeing the world like a chemist. So how can you tell when a chemical reaction is actually happening right in front of you? The great news is you don't need a fancy lab or a white coat. You just need to know what to look for. It's time to put on your detective hat because we're looking for 4 key clues. There are 4 big tells that give the game away. You might see a change in state, a totally new color appear, some unexpected bubbles, which means a gas is being created, or you might feel a sudden change in temperature. Let's see what these actually look like. First up, temperature. Imagine you take some little bits of zinc and add some acid. The test tube would actually start to feel warm in your hand. Now, that heat isn't coming from a flame or anything. The reaction is literally making its own heat. That's a classic sign that chemistry is happening. And you know what? That exact same reaction gives us our second clue. As the zinc and the acid mix, you'd see it fizzing, bubbles going everywhere. That's not just air, that's a brand new substance, hydrogen gas, being born right there. Seeing bubbles is a dead giveaway that atoms are on the move. And our third clue is often the most dramatic one, a change in color. For example, there's this compound called silver chloride. It's a perfectly white powder, but if you just leave it out in the sun, it slowly turns gray. The sunlight is causing a reaction, breaking it down into something new. New substance, new color. Simple as that. Okay, now, describing all of this in long sentences every time would be a total pain, right? It's slow and clunky. So, just like a chef has a shorthand for recipes, chemists created their own universal language to show exactly what's going on in a reaction. Let's see how that works. We can start with a full descriptive sentence, but we can simplify that into a word equation. This is way better. Our starting ingredients, the reactants, are on the left, and what we end up with, the product, is on the right. But the real pro move is the chemical equation. With just a few symbols, it tells you the entire story in a tiny bit of space. But here's the catch. A chemical equation is not just a casual list of ingredients. Oh no. It has to follow the single most important rule of accounting in the entire universe. It has to be balanced. And that rule is called the law of conservation of mass. And really, it's pretty simple. It just means you can't create atoms out of thin air, and you can't make them vanish into nothing. Every single atom you start with has to be there at the end. They just get shuffled around into new arrangements. Let's look at the reaction for rust as an example. If we do a quick head count of the atoms, we've got a problem. See the iron, or Fe? We start with 1 atom on the left, but somehow end up with 3 on the right. Where'd the other 2 come from? Same for oxygen. 1 goes in, 4 come out. This equation is totally unbalanced. It breaks that fundamental law. So how do we fix this? Well, we can't change what the molecules are, but we can change how many of them we use. We do that by adding these big numbers out front, called coefficients. So by saying we need 3 iron atoms and 4 water molecules, look at the counts now. 3 irons on each side, 8 hydrogens, 4 oxygens. Everything matches perfectly. The atomic books are balanced, and the universe is happy. Okay, so now that we can speak the language of chemistry, let's meet the main families of reactions. You might think there are countless different types, but most of them actually fall into just a few main categories. It all comes down to how the atoms decide to rearrange themselves. First, you've got your get-togethers and your breakups. A combination reaction is pretty much what it sounds like. 2 or more things combine to form one single, more complex thing. On the flip side, you have a decomposition reaction. That's where one big compound breaks apart into two or more simpler pieces. Then, things get a little more dramatic. Think of it like a dance floor. A displacement reaction is when a more reactive element comes along and cuts in, bumping another element out of its partnership. But a double displacement is even wilder. It's like two couples on the dance floor just decide to swap partners. Everyone goes home with someone new. And remember our first clue, a change in temperature? Well, that's what these two types are all about. Exothermic reactions are the ones that release energy, making things feel hot. The respiration that powers your body is a perfect example. The opposite is an endothermic reaction. It absorbs energy from its surroundings, which can actually make things feel cold. Now, to bring all this home, let's zoom in on one of the most common and important types of reactions, one you see literally every single day. Let's talk about oxidation. At its heart, oxidation is super simple. It's just what happens when a substance gains oxygen. That's it. For instance, when you heat up a piece of copper, it reacts with the oxygen in the air and gets a black coating of copper oxide. We'd say the copper has been oxidized. But you're definitely more familiar with other names for this process. Corrosion, like when iron rusts, that's just a slow oxidation reaction. And that gross, stale taste and smell from old chips or cooking oil, that's a process called rancidity, and it's caused by the fats and oils getting oxidized by the air. So how do chip companies fight back against this? With a pretty brilliant bit of chemistry, actually. You know how chip bags are always puffed up? They're not just full of air. They flush those bags with nitrogen gas. By pushing all the oxygen out, the oxidation reaction can't even get started. It keeps your chips perfectly fresh. You know, this quote really sums up what we've been doing today. Just knowing a fact like iron rusts isn't really science. That's just an observation. Science is understanding the story behind it, the language, the rules, and the patterns of the chemical reaction that makes it happen. And that's really the main takeaway. You're now equipped to see this hidden story playing out all around you. From a burning candle to a rising loaf of bread, you know the clues to look for. You know the language. So, with your new detective skills, the only question is, what chemical reaction will you spot next?